All right, we're in section 8.4, looking at computing partial derivatives algebraically. So to compute a partial derivative, we're not doing anything too different than what we've done before, so the rules of differentiation are still going to apply. We're basically going to be adding one additional kind of wrinkle into the computation. So to compute a partial derivative, we differentiate with respect to one variable and hold the other variable fixed. Okay, so to compute the partial derivative with respect to x, we hold y fixed, and to compute the partial derivative with respect to y, we hold x fixed. Now, we talked a little bit about fixing variables in the last section, but what does it mean to hold them fixed? It means to treat them as a constant. Okay, so when we say holding a variable fixed, we mean treating it as a constant. So what that means is you're going to have to use your imagination a little bit when you're differentiating here. Because if I want to find the derivative, the partial derivative with respect to x, I'm going to use x as my variable, and y is going to be treated like it was a number, okay, like it was a constant. So, for example, if we were differentiating normally, right, with a single variable, the derivative of x squared would be 2x. But if I'm differentiating with respect to y, and x is not the variable, then x squared, well, if x is a number, x squared is just a number, and the derivative of x squared would be 0 with respect to y. So let's look at this example down here. Hopefully this will kind of give you a good idea of what we're doing. So for fx of xy, if we take the derivative with respect to x, so x is the variable, y is a constant, derivative of x squared is just 2x, derivative of 5y squared, well, 5 is a number, y is being treated like a number, it's a constant, so that means that this whole thing is just one big constant, and the derivative of a constant is 0. So you could just put plus 0, you don't even have to put plus 0, right, because we don't need to show that we're adding 0. But that would be it. That's the partial derivative with respect to x. So you take the derivative of all the x's and then just treat the y's as constants. Okay? So to get fx at the 0.32, now we just plug in the 0.32. So this is 2 times x. So x is 3 in this case, so that's 6. Okay, and then for fy, well, in this case, x is a constant, so x squared is a constant as well, right? Because if you took, x is 5, for example, 5 squared is 25, that's still a number. So the derivative of x squared with respect to y is 0, right? So that would be 0 plus whatever we get from that second term. And then the derivative of that with respect to y is just treated as normal. So bring down the 2, so that's just 10y to the first. So then the partial at 3, 2, right? Y is 2, so that's 10 times 2, which is 20. So that's our partial derivative with respect to x and with respect to y. So let's look at a few examples. So find both partial derivatives of the following functions. Alright, so for the first one here, with respect to x, so we have 3x, so just take the derivative normally, so that's 3. E to the negative 5y, there are no x's in this at all. Does everybody see that? There's no x's here at all, which means that this whole thing is constant. If there's no variable in it, no x in it, it's constant. And so its derivative is 0. So that's it. This is fx. It's just 3. And then for fy, well, if x is constant, 3x is constant. So that's just 0, its derivative. And then this one now, derivative of e to the negative 5y, that's going to be, right, negative 5e to the negative 5y, right, using the chain rule. Okay, so those are our partial derivatives. Now let's see what happens when we get a product in here. So gx. So when we're taking the derivative with respect to x of this function, well, y is like a constant. So sometimes it can be helpful. Just pretend y is a number. You can just pick a number at random. Don't actually use that number in your calculation because that's going to give you a wrong answer. But just pretend that it's a number like 5. And so we would say, what is, the derivative of 5x squared? Well, you would ignore the 5, right? Just take the derivative of the x squared. And same thing here. We're going to just ignore the y because it's just a constant multiple. And we're just going to take the derivative of the x squared, which is 2x times the constant, times y. So we get 2xy for that derivative. gy, here we have x squared is the constant multiple now. So I have a constant times y. The derivative of the y is 1 times the constant. So that's just x squared. Okay, this takes some practice just to get used to dealing with these partial derivatives instead of just what we've done with single variable differentiation. But once you get the hang of it, it's basically just like taking single variable derivatives. So just with again this extra little mental check at the very beginning. So let's look at this next one. So we have hu of uv. And then hv of uv. So partial with respect to u. So that means this whole term with the v's in it is treated as a constant multiple of the u squared. So just differentiate the u and leave the v's alone. So that's just going to be 2u times e to the 2v. And then when we're differentiating with respect to v, well now the u squared is the constant, so we're just going to leave it alone. And the e to the 2v, the derivative of that is 2e to the 2v. So this is going to be 2u squared e to the 2v. Just like that. Okay. So now let's look at an example where we can actually compute partial derivatives now and put a bit of interpretation to this. So consider a small printing business where N is the number of workers, V is the value of the equipment in units of $25,000, and P is the production measured in thousands of pages per day. Suppose the production function for this company is given by P equals F of NV, which equals 2 times N to the 0.6 power times V to the 0.4 power. If this company has a labor force of 100 workers and 200 units worth of equipment, what is the production output of the company? Okay, so for part A, so the printing business, the amount of production they have depends on how many workers they have and how much equipment they're using. Okay, so the more workers and the more equipment that you're using, the more production you're going to have, right? So to find out at 100 workers and 200 units of equipment, that's F of 100 comma 200. So that is 2 times 100 to the 0.6 times 200 to the 0.4. Which is 263.9 thousand pages per day. Okay, so we have 263.9 thousand pages per day. That's how much they're producing at this current level, if they have 100 workers and 200 units worth of equipment. Okay, that's how much they're producing every day. Part B, let's find the partial derivatives with respect to n and with respect to v at this value of 100 comma 200 and interpret what these answers mean in terms of production. Okay, so Let me just split this up here. So to get the partial derivative with respect to n, so here's our function right here. So again, v is being treated like a constant here because n is the variable. So v is just going to tag along, and we're going to take the derivative of the n. Now we're going to use the power rule for this, right? So if we have n to the 0.6, we're going to bring the power down and subtract 1 from the power. So this is going to be 2 times 0.6 n to the negative 0.4 times v to the 0.4. So that would be our derivative, our partial derivative with respect to n. And now it wants us to evaluate that at the point. So at the point 100, 200. So that's going to be 1.2 times 100 to the negative 0.4 times 200 to the positive 0.4. Which is approximately 1.583. And that is 1,000 pages per worker. Okay, so this is the rate of change with respect to n, where n is the number of workers. Okay, so if we are currently at a level of production using 100 workers and 200 units worth of equipment, as the number of workers changes, this is how the production changes. Okay, so let's go ahead and put that in here. Okay, so if we have 200 units of equipment and increase the number of workers from 100 to 101, the production output will go up about 1,583 pages per day. Okay, so this gives us how much increased production we'll have by adding another worker, right, above our 100 workers that we already have. Okay, so then let's look at f sub v. Okay, so partial with respect to v. So we're going to treat this the same way that we did before. Okay, so we're using the power rule, except now v is the variable and n is the constant. So I'm bringing down the 0.4 and subtracting 1 from its power. So we get 2 times 0.4 times n to the 0.6 times v to the negative 0.6. Alright, so FV at our point in question, 100, 200, and that's going to be 0.8 times 100 to the 0.6 times 200 to the negative 0.6, which is approximately 0.53 thousand pages per unit of equipment. Oops. Okay, so we get about 0.53 thousand pages per unit of equipment that we add. So let me go ahead and just add our explanation here. So if we're currently at our current production level, so if we have 100 workers and increase the value of the equipment from 200 to 201 units. So remember, a unit is just $25,000. So basically, if we increase our equipment in value by $25,000, okay, the production goes up by about 530 pages per day. There we go. So if we have 100 workers and increase the value of the equipment from 200 to 201 units, production goes up by about 530 pages per day. So as you can see, it is more effective having an additional worker as opposed to additional machinery, right? The worker gives you more pages per day, but when it comes to decision making, if you're the one running this business, you think, okay, well, the worker is getting me about 3 times the production, but think about the difference in expense, right? Because the machine is a one-time cost of $25,000. The worker, depending on like what state you're in, right, and what the value of the job is, you could be paying them, $50,000, $75,000 a year. So over the life of that machine, if the machine even lasts like 10 years, that's still $25,000 for the whole thing, as opposed to paying hundreds of thousands of dollars to an employee over those years. So you have to weigh the increased production with your increased costs. And those are decisions that can be made on that business level. But just kind of put that into perspective a little bit. But that's what those partial derivatives give us. Again, rate of change with respect to one variable holding the other one as a fixed value, right? So just looking at how does increasing my number of workers impact production, and then just looking at how does my equipment level impact production, looking at them one at a time. Okay? And then the last thing here for this section, we can also talk about second order partial derivatives. So just like with regular single variable derivatives, you can take multiple derivatives, right? Second derivatives, third derivatives, etc. But with partial derivatives, you always have to indicate which variable you're differentiating with respect to. So if we take the derivative with respect to x and then x again, that we write fxx. Okay, or you can take the derivative with respect to x and then y, that's fxy. Or if you take the derivative with respect to y and then again with respect to x, that's fyx. Or if you take the derivative with respect to y and then again with y, that is fyy. So those are the 4 second order partial derivatives. Okay, so let's actually try them in this example here. So here's our function. So let me get the first orders first. So fx and fy. So partial with respect to x. So y is a constant, so the derivative of that x is just 1. This is a constant, so the derivative of that x is 2x. The 2 times the 3 gives us 6. So this is just going to be 1 times y squared plus 6x e to the y. Okay, so that's going to be partial with respect to x. With respect to y now, x is the constant, so that's just going to be 2xy plus derivative of e to the y is just e to the y, and then this is a constant, so it just goes along for the ride. So plus 3x squared e to the y. So that one doesn't change at all. All right, so those are our first order partials, so fx and fy. So now, to take the second order partials, we just take partial derivatives of these. Okay, so that's all there really is to it, is just taking more derivatives of previous derivatives. So, let's get fxx. So derivative of this function with respect to x now, that has no x's in it, which means it's just all constant, so the derivative is 0. And this one, derivative of x is 1 times all those constant terms. So this is just 6e to the y. And fxy, well, derivative of, again, this function with respect to y, that's 2y plus 6x e to the y. Okay. And then for our second order partials on this side, we have fyy, so we take the partial with respect to y, and then take its derivative again with respect to y. So y is the variable here, so that's just going to be 2x times 1, plus the derivative of e to the y is just e to the y, so that's just going to stay exactly as it is. Okay, and then the last one here, fyx. So derivative of fy with respect to x this time, so x is the variable, y is the constant. So that's going to be 2y plus derivative with respect to x, that's going to be power rule, right, bring down the 2. That's going to be 6x e to the y. And those are our 4 second order partials for this example. Okay, so we can compute partial derivatives of partial derivatives. Now, does anybody notice anything interesting about any of these? Hopefully you might notice that these two are actually the same. And it turns out that as long as these partial derivatives, these second orders, are continuous at the point AB, then this will always be the case. Okay, so you will have, this is a valid relationship all the time, as long as you have valid functions, where fxy at a point equals fyx at the point. Okay, so this is a very nice relationship because all you have to do is find one or the other. Okay, you don't have to find both because as long as the functions are continuous, right, they're valid functions, this will always be the case. So you'll always have that those are the same. And, that can always be a good check to make sure that you did a problem correctly, just to get both of them and make sure that they are the same. So that can be very useful. But that brings us to the end of section 8.4, our kind of introduction into the calculation of partial derivatives. When we come back next time in 8.5, we're going to look at more calculus that we're going to be performing using these partial derivatives. So I'll see you all next time.